Now we start on the sorts themselves. The first one is insertion sort, the same motion you use when you sort a hand of playing cards. Insertion sort takes each element in turn and slides it left into its correct spot. The spot is somewhere in the part that is already sorted. It is exactly the playing card motion from the opening. 3 ideas make it work. The prefix A from index 0 to index I minus 1 is always sorted. That is the invariant. We take A at index I, the next card, and shift every larger value in the prefix 1 step to the right. Then we drop the card into the hole once nothing bigger stands in front of it. We shift only elements that are strictly greater than the key. That is what makes insertion sort stable. An equal element never gets shifted past, so 2 equal keys keep their original order. Let's read insertion sort in pseudocode. The outer loop runs I from 1 up to n-1. We save A at index I in a variable called key. We set J to I-1, so J points at the last card in the sorted prefix. The while loop runs while J is at least 0 and A at index J is greater than the key. Inside it, we copy A at index J 1 step to the right into A at index J plus 1, and then we decrease J by 1. When the loop stops, we drop the key into A at index J plus 1, the hole we just opened. One small detail matters. We compare with greater than, not greater than or equal to. If we used greater than or equal to, an equal key would shift past its twin, and stability would break. Let's sort the array 5, 2, 9, 1, 5, 6. The indigo cell on the left is the sorted prefix. Right now it holds just one value, 5. It is a sorted list of 1. Everything to its right is unsorted. Pass 1. We lift the key 2 and hold it. 5 is greater than 2, so 5 shifts right, shown by the arrow. Then we drop the key into the front in green. The sorted prefix is now 2, 5. Pass 2. The key is 9 in green. 9 is greater than 5, so nothing shifts. 9 is already in place. The sorted prefix grows to 2, 5, 9. Pass 3. We lift the key 1. It is smaller than everything before it, so 2, 5, and 9 all shift right. That is 3 arrows. Then 1 drops into the front in green. The sorted prefix is 1, 2, 5, 9. Pass 4. The key is 5 in green. We shift the 9 right and then stop. The next value to the left is the other 5. It is equal, not greater, so the key does not jump past it. It lands just after its twin. This is why insertion sort is stable. Pass 5. The key is 6 in green. We shift the 9 right, then drop 6. The sorted prefix is 1, 2, 5, 5, 6, 9. Done. The indigo prefix is now the whole array. It is fully sorted, 1, 2, 5, 5, 6, 9. Predict, then reveal. 1 pass of insertion sort on the array 5, 2, 8, 1. Write down the array after I equals 1 finishes before you advance. Here is the answer. The key is at 1, which is 2. 5 is greater than 2, so 5 shifts right and 2 goes to index 0. The array is now 2, 5, 8, 1. The 8 and the 1 have not been touched yet. The C code maps 1 to 1 onto the pseudocode. The outer for loop runs I from 1 up to n. We copy A at index I into key, the next card to insert. We set J to I the while loop runs while J is greater than 0 and A at index J minus 1 is greater than the key. Inside, we copy A at index J minus 1 into A at index J, shifting it right, and then we decrease J by 1. When the loop stops, we write the key into A at index J, its sorted spot. Now the cost. In the best case insertion sort is big O of n. on input that is already sorted because the inner while loop never runs even once. That property has a name. It is adaptive. On average, and in the worst case, it is big O of n squared because reverse sorted input shifts everything on every pass. It is stable, and it is in place with big O of one extra space. The full program is in the Insertion Sort file.